So the next series of reactions that we need to study are those better known as oxidation-reduction reactions. Sometimes these are referred to as redox reactions or single displacement reactions or even metathesis reactions. And essentially all these terms mean the same thing. There is going to be a species in reactants that pertains to a particular atom, and that atom will undergo oxidation, whereas another atom in reactants will undergo chemical reduction. So before we start looking at rules of assigning oxidation numbers, let's briefly discuss what the terms oxidation and reduction mean. For example, oxidation can mean, on one hand, to be the loss of electrons, the loss of hydrogen, or the gain of oxygen, which is really where we get the term oxidation. Reduction, on the other hand, is going to be the polar opposite. We can talk about the gain of electrons or hydrogen, or the loss of O2. There are several good mnemonics that can help us to remember these definitions. One of my personal favorites is Leo the lion says, and everybody say it with me, grrr. Or if you want to go all 90s, Leo the lion says, grrr. Loss of electrons is oxidation. Gain of electrons is reduction. We can also go with oil rig. Remembering that electrons are going to be involved in current, and the physical symbol for current is I. Oxidation is when I lose current. Reduction is when I gain current. So either of these two definitions work just fine to help us memorize, master the difference between oxidation and reduction. Now, we can talk about, in the context of a chemical reaction, and I guess the best way of learning this is, let's look at a specific reaction. So let's say that a strip of magnesium metal is immersed in dilute hydrochloric acid. So in writing the molecular equation, we would have Mg. Now this is a metal, so of course it's going to be a solid. We would have HCl dissolved in water, which would be aqueous. When we react a strong active metal with a strong acid, we will always generate hydrogen gas. I covered this at the very end of lecture last week. And we will get a metal halide salt. Now, we want to ionize where we can. Mg metal is not solvated by water. We have H plus Cl minus yields H2 gas plus Mg2 plus 2Cl minus. Of course, when we begin to balance, now my equation is balanced on both sides. I can cancel out spectators, which will be the 2Cl minus. And what I'm left with is my net ionic equation. In this case, Mg solid plus 2H plus. This, of course, will be aqueous. Produces H2 gas plus Mg2 plus aqueous, which will give me my net ionic equation. We can even take this a step further and draw a molecular cartoon. So if I have a strip of magnesium, notice the magnesium atoms are surrounded only by other magnesium atoms. H plus are going to be surrounded by water molecules, so I'm going to draw a sphere of solvation. Remember, this is a cartoon, so we don't have to be perfectly accurate. It's just a model. And of course, Cl minus and the Cl minus will also be surrounded by water. And so this is my what my molecular cartoon will look like just before a reaction occurs. After the reaction occurs. Now I have Mg2 plus that will be surrounded by water. I'll also have Cl minus surrounded by water. So since I have 8 magnesiums, I need 16 chlorides. All the chlorides are going to be surrounded by water as well. So notice chloride was surrounded by water before, surrounded by water after. And then H2 gas. And this is a complete molecular cartoon of the net ionic equation. So where the environment doesn't change, in this case, Cl minus is the same before and after, we know we have a spectator. Now, let's look at how we might go back and assign oxidation numbers to these chemical species. So what I'd like to do is simply redraw the molecular ion equation, and then let's go through the steps that we need to make these assignments. Mg solid plus 2HCl aqueous yields H2 gas plus MgCl2 aqueous. So let's take a look at our lecture note slides and let's start to determine how we assign these oxidation numbers. So oxidation number rule number 1 I think is only common sense. If I have a monoatomic ion, the charge of the atom is the charge of the ion is the oxidation number of the atom. So when I have Mg2 plus, it has an oxidation number of +2. If you have an element in its standard state, the oxidation number is 0. Oxygen will nearly always have an oxidation number of -2 unless it's a peroxide or a superoxide, in which case oxygen has a charge of -1. This will happen very, very rarely in the context of chemical reactions in inorganic chemistry. Hydrogen will always have an oxidation number of +1 unless it's bonded to an alkali metal, in which case it's a hydride, and will have an oxidation state of -1. Halogens will always be -1 unless they're bonded to oxygen. Fluorine will always have an oxidation state of -1, no exceptions. If you have a compound, the sum of all the oxidation numbers has to equal 0. If you have an ion, the sum of all the oxidation numbers comprising that ion must equal the charge of that ion. Let's work a quick example. Let's determine all the charges of all of the atoms in potassium permanganate and also in dichromate ion. So what I'm going to do is do the examples first, and then we'll go back to these rules. So if we have KMNO4, which has a charge of -1. Oxygen will be -2. It's not in a peroxide. There are 4 oxygens, therefore oxygen brings a total charge of -8. Potassium is an alkali metal, it will always be +1. So I have 1 minus 8 plus x equals -1. When we solve for x, x must be equal to +7. That is the oxidation number of manganese. Let's move to a different example. Cr2O72 minus. Again, each oxygen will be -2. Since there are 7 of these, that's -14. Now I have 2 chromium, so that's I add 2x to -14, and I must get -2. So 2x equals 12, x equals 6. The oxidation state of each chromium is +6. Now let's take this and move back to our previous example. Magnesium is in its standard state, 0. Hydrogen, its standard state, 0. Cl minus would be -1. H would be +1. Magnesium +2 because it's an alkaline earth metal. Each chlorine -1. Magnesium is oxidized because I go from magnesium to magnesium 2+, which means it must lose 2 electrons, and I do this to balance the charge. 0 in reactants, 0 in products. This is better known as the oxidation half reaction. In the reduction half reaction, I have 2H+ that goes to H2. And I need 2 electrons to balance the charge. I can directly add these together because the electrons will cancel. And notice I get the overall stoichiometry. Magnesium plus 2H+ yields H2 plus Mg2+. So this is how we actually apply the calculation of these oxidation numbers into a real live chemical situation. So this at least springboards us into an intelligent discussion in class this evening. This is certainly something you'll want to practice, and practice quite a lot.